Now what one can do is, if I want to eliminate the harmonics, see all these filters are the AC side filters to eliminate the harmonics or minimize the harmonic components in the current. So the dominant harmonic is the most dominant harmonic. What is the most dominant? 11th. Please note we are using a 12 pulse converter in practice. So the 11th harmonic is the dominant harmonic. So I can use single tune filters for some dominant harmonics, say 11th. I can use one for 11th, one for 30. See, it will work for only one frequency. That's why it's called single tuned. So I can use it for one dominant frequency. If I want for another dominant frequency, the next one is 13th. I should use one more single tune filter. Then the next one is 23rd, one more, 25th, one more. But there are infinite number of harmonics. So we will not be using infinite number of filters. We will use a few single tune filters for a few dominant harmonics, and for the rest we will use one single filter, which is a damped filter, which will try to filter out all the remaining harmonics. Okay. Now instead of that, what one can do is, instead of a single tune filter, we can also have what is known as a double tune filter, which will act to minimize two frequencies. So it will do the job of two single tune filters. Okay. So I can have, instead of two single tune filters, one double tune filter. Now I will just give the circuit diagram. We will then see how it works. See, double tune filter is having a circuit like this. So obviously there should be two inductors and two capacitors, but how the two inductors and capacitors are arranged is like this. So there is also a resistance. So it's a two terminal device where I have two capacitances C1 and C2 and two inductances L1 and L2, and suppose this resistance is R. So I can as well have this arrangement. This is what we have already studied, single tune filter. Suppose I have R1 L1 C1, R2 L2 C2. This is two single tune filters. Now instead of this arrangement, we can have what is known as a double tune filter. Now I mean, there may be some reason, there should be some reason for using a double tune filter instead of two single tune filters. Single tune filters are obvious. I mean, why one should use a double tune filter? Okay. Do you see any advantage? Now, when a filter, suppose I take a single tune filter, it is subjected to impulse. So which element is subjected to impulse? See, I have an inductor and a capacitor in series. Forget for the time being resistance. So which among the two is subjected to impulse? Inductor. But it's the inductor which is subjected to the impulse. Now both inductors are subjected to the impulse if I use two single tune filters. Now look at the circuit of double tune filter. If there is an impulse, then there is only one inductance which is subjected to impulse. Which one? Which one? No, the answer you gave for single tune can be used to give the answer for this. Huh? L1. It is L1 because L2 is across the capacitor. So L2 is across the capacitor. So if there is an impulse, only L1 needs to be designed for the impulse. So that advantage is there. Of course, there are a few other advantages. One can get into the details and try to show that the power loss at fundamental frequency is considerably reduced in the double tune filter. So we will not get into all those details, but there are some advantages. So this is a double tune filter. Okay. Now the question is how is this double tuned filter supposed to behave? See, in the case of single tuned filter, so if I take a single tuned filter, suppose I plot the magnitude of the impedance of the filter as a function of frequency. Okay. So, it is somewhat like this. There is at one value I get a minimum value of impedance. What is that minimum value for single tune filter? Huh? What is this value? The minimum value of the filter impedance for a single tuned filter. At some frequency it is minimum. Huh? Resonant frequency. What is the value of the impedance? It is equal to R. It is R, that is all. It is just R. Okay, the effect of inductance and the reactances of inductor and capacitor will be same at the resonant frequency. Now, for a double tuned filter, the graph is like this. If I plot as a function of frequency the magnitude of the filter impedance, then I get 2 minima. Instead of 1 minima, I get 2 minima. So, it is somewhat like this. Okay. So, again these two values of frequency at which I have minima are known as the resonant frequencies. So, these two are called resonant frequencies. So, what I would ask you to do is try to get an expression for the resonant frequencies. Of course, one can make a simplification, neglect R. See, neglecting R means, what is meant by neglecting R? R is, no, from the context you should try to make out what is meant by neglecting R. Open circuit, infinite impedance. Neglecting R means R has infinite value. So, if I neglect R, then it becomes very simple. Then at the resonant frequency, what will be the impedance if I neglect R? It will be 0. It will be 0. So, try to find the expression for the resonant frequencies by neglecting R. But when I have more than one frequency is to be damped, I can't be using only tuned filters. So, what I will do is, instead of using many tuned filters, we will restrict our number of tuned filters and use one another filter called damped filter. So, it is a high pass filter, that means all the high frequencies will pass through that. A damped filter is like this, it has a capacitance, inductance and a resistance connected across the inductor. The resistance is connected across the inductor. So, if you look at this plot of magnitude of impedance as a function of frequency. So, here suppose, okay, let me call this capacitance L, inductance capacitance C, inductance L, resistance R. So, here as the frequency increases, the impedance decreases, reaches a minimum, then slightly increases and approaches a value. Okay. So, it is essentially having a very low impedance for all frequencies beyond a certain value. So, beyond a certain value of frequency, it will have very low impedance. Now, this is in contrast with the tuned filters, where the impedance is low at only a small range of frequency around the resonant frequency. So, it will approach some value. What is the value? So, the magnitude of the impedance approaches some value. What is that? It will approach some value. What is that? As frequency tends to infinity, what is the limit of magnitude of ZF? Look at the circuit. R. It's R. Okay. L becomes an open circuit, C becomes a short circuit. So, it's R. Okay. So, it's essentially having a constant impedance for all frequencies beyond a certain value. So, we can use a few single tuned filters, undamped filter, or double tuned filters, undamped filter, any combinations.